Okay, let's get started. Today we will have motion planning lecture number 6, and our topic will be tree-based motion planning, and we will also talk about optimal motion planning and especially asymptotically optimal motion planning because it relates to sampling-based planning. Before I start, just a small recap as usual. So where are we currently in the lecture series? We are currently at the sampling-based planning stage, which is one of those 3 topics which we had. One was search-based planning, one is optimization-based planning, and today we will still talking about sampling-based planning, and we will do that for the next 3 lectures. Then we will have 2 lectures of optimization-based planning, and then finally we will compare all of them, and we will also talk about more exotic approaches, for example, to multi-robot or to hybrid planning. Okay, and last week we talked about probabilistic roadmaps, which was one of the, I would say, first approaches to sampling-based planning, and also one of the most famous ones, and one which is very well working. And today we will talk about, I would say, the second biggest approach to sampling-based planning, which is tree-based motion planning. And we will specifically talking about RT, which is standing for Rapidly Exploring Random Tree, which is, I would say, one of the most famous algorithms in motion planning. And I would say everyone who tries to solve a motion planning problem, they usually start with RT because it works so well in practice. We will also have a little bit of an introduction to asymptotically-optimal planning, just how you set up a planning problem if you want to have an optimal solution, and how you can actually achieve asymptotic optimal planning with some of the standard algorithms. And then we will talk a little bit about optimal tree-based planning, and we will talk about RT star and bit star, which I would say are, again, 2 of the most famous planning algorithms for actually doing optimal motion planning and especially optimal tree-based motion planning. So that is the general idea for today. And so let me start with tree-based motion planning. As I said, today we will talk about one of the most famous algorithms in motion planning, which is the Rapidly Exploring Random Tree, the RT algorithm. And originally invented was that by Steve Laval, and there was also a prior publication by David Zhu. So both of them, they basically introduced trees to motion planning and to solve motion planning problems. And it turned out that this was, I would say, one of the most efficient ways of how you can solve very difficult motion planning problems. And the idea behind it is very, very simple. So what you do is that you are starting at your start configuration, and then you try to grow a tree through your configuration space, and you do that by doing some random walks, some random extensions in different directions. And in that way, you try to grow the tree, you try to explore the configuration space, and then hopefully at some point you reach your goal and you're done planning. And this RT algorithm, here's some pseudocode for that. So as you can see, it's actually pretty simple. If you look at it, as an input to the RT, you get a start configuration and a goal configuration. And usually you also have a parameter, which we call mu here, which tells you how far you are extending the tree at every step on your way. Because, as we will further see, this is actually quite beneficial to have a more uniform covering of the configuration space. And then what you do is that you have this tree, which we represent as V here. And in the beginning, you add just a root node, the start configuration to your tree. And then you just iterate while you're not finished. You're sampling a random configuration in your configuration space. This is your xrand. Then you try to find out what is the nearest configuration in your tree. This is xnear to your just randomly sampled configuration. And then what you do is that you steer your tree, your nearest neighbor in your tree, towards this random configuration. And usually you cap it at this mu parameter so that you are steering only a certain distance into this direction. And this gives you a new configuration. And if this configuration, if you made some progress, then you add this tree to your node, you add an edge to your tree, and then you just check if you have actually reached your goal, if the distance between your new configuration and your goal is smaller than some epsilon, and then you return a path from your tree. So this is a general idea, and let me give you some visual example of how this actually works. So I have here a 2D configuration space. In gray are some obstacles, and we have a point robot, and the point robot starts at the green configuration here, and it wants to go to the red configuration. And we want to solve this with an RT, and so the idea here is that you are starting with your start configuration as your tree, and then you sample a random configuration in your configuration space. So for example, it could be this configuration up here. And then what you do is that you are checking which one is the nearest node in your tree. So of course, in the beginning, you have only one node here in your tree, so this will be your nearest neighbor. And then you try to extend from this nearest neighbor to your configuration in this direction here. And as I said, usually we have this parameter mu, which tells you how far you can go into this direction. So this will be this circle here around the nearest neighbor. And this will give you a new configuration, which we call x new. And if this configuration is valid, and if this edge between your nearest neighbor and your new configuration is also valid, then you will add it to your tree. And so this was one iteration of this RT. You basically sampled a configuration, you made one step into this direction, you get a new node here, and you add it to your tree. And in the same way you continue, you again sample another configuration in your configuration space. You find out what is the nearest neighbor. So in this case here, it might be this one. You go again into this direction. And if you can't actually go all the way into this direction, if there's an obstacle here, then you stop before the obstacle, and you return this configuration here. And then you check if this edge between your nearest and your new one is valid. And if it is valid, then you just add it to the tree. So this was the second iteration, and then you can just go on in the same manner. You sample again, you find the nearest, you extend it into this direction, you sample again, and sampling doesn't take validity into account, bless you. So for example, you can also sample something inside of an obstacle. So usually you don't care because you're only making steps into this direction. And then again, you make another step into this direction, you sample again, you find the nearest, you make a step into this direction, you find a new one. And so in this manner, you grow your tree to your configuration space. And this goes on and on and on until suddenly you find a configuration which is exactly in your goal region. And in that case, you are actually done. You now have found that one of the configurations here is inside of the goal region, and that means you can just backtrack from here. You can just go to the parent and to the parent and to the parent, and this basically gives you a tree, a path through your tree from start to goal configuration. So this is the general idea. You grow this tree until you find the goal region. And the main reason why this algorithm is actually so efficient is because it has this implicit Voronoi bias. So let me just tell you a little bit about this Voronoi bias. So you might remember what a Voronoi region is. It's basically if you have a set of configurations or points in a space. Let's say you have Q1 and Q until Qk in your configuration space Q. Then the Voronoi region is basically defined as all the configurations which are nearer to a certain configuration from your set of configurations for all possible configurations which you have here in your set. And so this gives you this nice covering of the configuration space where each of the points has an associated region, and this region here contains all the points which are nearest to the specific point here in this region. So for example, this green region here, it contains all the points which, if you compute, for example, the nearest neighbor, you would get this single point here. And so yeah, as I said, with RT, you sample a random configuration. And as you can see here, usually the regions which are bigger, they will have a higher probability that you sample in them, which means that you have also higher probability that you will extend those nodes which have higher Voronoi region. And in this way, you will very quickly cover actually, yeah, the largest regions of the state space. And this makes actually a tree grow very fast. And you can see this here, for example, on this slide where we have RT in two configurations, one where you have 45 iterations and one where you have 390 iterations. And you can see here, because we have this Voronoi bias, we first grow the tree in all directions of the configuration space. We first get like a very non-dense covering of it. And then if you actually spend more and more time on your tree, you will actually have a finer and finer resolution of the tree. And so this is a very nice way to first quickly get a good overview about your whole configuration space. And only if you can't find any paths there, then you can actually go into like the finer details and try to explore like smaller passages or something. And because this probability of being selected is proportional to this Voronoi region in the tree, you have this what we call exploitation trade-off, where you basically have this trade-off between should I first explore the whole space or should I actually exploit my tree and go maybe a bit finer into the details, refine my tree, go into smaller corners of the configuration space. And so what the RT is actually doing here, it's first trying very, very hard to explore the whole space as quickly as possible. And once it has like a good covering, like in this case here, then it would go into this exploitation phase where it would find smaller and smaller parts of the tree, and it would show you this more fine-grained, finer resolution tree in the end. So this is the number one reason why RT is actually so successful, because it makes a lot of sense to first explore the whole space, because very often your goal configuration might be in a very large portion of the configuration space, and it makes sense to first try to find out what are all the bigger portions of your configuration space before you actually go into the details. Okay, so I would say this one, is the most basic algorithm, the most vanilla version of RT. And of course, there are several improvements possible. Before I go there, maybe, does anyone have any questions about RT? No? Everything makes sense? Cool. Yeah. Then let's talk a little bit about improvements. So while RT is pretty efficient, there are some things which don't work so well in this basic version. So one is, of course, that you are just randomly searching blindly through your configuration space, and you're not taking the goal region into account. And so it obviously makes sense to also extend your tree towards your goal. So this would be one improvement. Another improvement would be that you explicitly sample your goal region with a certain probability. So instead of always sampling the whole configuration space, you spend a little bit of time with a certain probability to sample only the goal region. And then another improvement is also to have not only one tree to grow through your configuration space, but you have two. You have a bidirectional tree where you grow from your start and from your goal, and you try to connect those trees together. Yeah, let me show you some visuals of how this works. So of course, if you have this extension towards a goal, then periodically, maybe in every iteration, you try to check if you can extend your tree towards your goal. So you do that by just computing the nearest neighbor to your goal, and you try to make a connection here. And if this connection is actually valid, then you add it to your tree and you're done. And so it makes a lot of sense to check from time to time if you can actually extend your current tree towards the goal, because of course it's very difficult sometimes to just grow the tree randomly here and then hope that at some point you actually hit the small goal region here. Another approach is to have a goal bias in sampling. So that means basically that from time to time you sample configurations which are inside of this goal region. So if you have only one goal, then you always take this goal and you try to again extend the tree towards the goal. So this is very similar to this extension step, but it's a bit more general because your goal region can also be something which is a bit bigger or a bit more complicated than just a single configuration. And so in this case here, you just sample from this goal region, you try to connect it, and from time to time, you check here again if you can reach it. Okay, and if you take this idea to the extreme, then of course, it would make sense to actually also start growing a tree from your goal region. So this is what a bidirectional RT would do. You start here again, and you would, in each iteration, choose one of your trees, either randomly or you just change them. And in this way, you grow 2 trees here. And then in every iteration, or every couple of iterations, you try to check if actually the trees can be connected to each other. And if they can, you connect them, and then you can just create a path by starting from one of your trees, going to your connection point, and then going from the connection point to your start. And the way of how you actually connect them is that you take the latest configuration which you have just added to one of your trees. You try to you compute the nearest neighbor in the other tree, and then you try to connect them. So this is a very simple way of how you can always check if 2 trees are connectable. And I would say this is really, with all those improvements here, the best way to actually solve complicated motion planning problems. Especially if you are starting from a very tight or narrow passage, then growing 2 trees usually makes a lot of sense. Okay, so I would say those are the most obvious extensions which you can do. There are also some other improvements which you can apply. So one is this path shortening, which we also talked about when we talked about this probabilistic roadmap. Because the output of an RT is usually also not very smooth. You have always those zigzag motions, and so usually it makes a lot of sense to do a little bit of smoothing, a little bit of path shortening afterwards. Another extension is to not only grow 2 trees, but you could also, for example, grow multiple trees. Maybe you would start one of the trees in the middle between start and goal to just accelerate planning, and very often this works pretty well. But I think there's not so much improvement to be gained by having multiple trees. So in practice, usually people use only 2 trees because it's enough. But there are definitely also some approaches out there which use multiple trees. And then, of course, another improvement is targeted sampling, where you just try to sample not only randomly in your configuration space, but you try to exploit somehow the geometry of your environment to sample on those locations where it makes sense or where you have narrow passages. So for example, if you look here, you would maybe not try to sample a lot in those free regions here of the configuration space, but you would try to do something a bit smarter, maybe something where you try to always sample in between obstacles here, and you have a function which tells you how close you are to obstacles, and you try to have more samples in those areas to improve planning performance. Okay, yeah, so I would say this is everything about RT and also everything about what you can do as improvements. Of course, there's a large literature about RT, so there are a lot of more things which you can actually do, but I would say those are really the basic ones. And already this version works pretty well, so in practice usually you don't need any more additional improvements. Okay, any questions about RT improvements, tree-based planning?
What's the best way to do the path shortening part?
Mm-hmm.
I think we touched it last time, but
Yeah, so the basic version of it is just that you are randomly sampling 2 points on your path, and then you try to connect them, and if they are connectable, then you just add them as an edge and you delete everything in between. Usually there are some more tricks which you have to do, because if you do that very often, you get a lot of very small spaced points here, because you can always like improve it a little bit more. And so usually you have also a function, for example, to collapse 2 very close points together, something like that, to improve performance. And then of course later on we'll also talk a little bit about smoothing, because here you also still have like this zigzag motion. Even if you're shortening stuff, you still have the zigzag motion. And so very often you would also try to come up with something like fitting a Bezier curve or so through all the points, and then try to check if it's still feasible. And this would definitely improve smoothing. And then later on also execution time. Yeah. Any other question? Cool. Okay, so this was tree-based planning for, I would say just basic motion planning. And now I want to talk a little bit about how you can actually do motion planning with sampling-based approaches in an optimal setting, where you want to not only find any solution, but you want to find the global optimal solution to your planning problem. And this brings us to the topic of asymptotic-optimal motion planning. And I would say the first question which we need to answer is, what is actually optimality? And there are different definitions of that, but from a higher level, it's basically that you have the property of a planner to return a motion which surpasses all other motions in quality. You can also define it in more mid-level terms, that you say, for example, that from all possible paths which you could compute, you return the one which minimizes an objective function. Or you could also give a more mathematical, exact definition, where you say, okay, if you are given a motion planning problem with a state space, with a start configuration and a goal configuration, you want to find a solution path, usually we call it P star, which minimizes an objective cost function C. And this cost function should be in such a way that the cost for the solution path P star should always be smaller or equal to all the paths which are possible for this motion planning problem, and the cost of those paths. So you would try to really return the path which minimizes some cost functions for your problem. And so this is the way of how we define this. And the second question which you might have is, why do we actually need optimality? Isn't it enough if we just have a feasible solution? And usually there are multiple reasons why you would want to have optimality. One is, for example, aesthetics, that you don't want a path which goes all the way through your configuration space, but you want maybe some where you just have a smooth execution of your robot. Another reason could be efficiency. If you have a lot of robots, larger teams, you want to also solve problems as efficiently as possible, because that could mean you solve a task in less time, and that, of course, makes more money. And so, of course, you want to have the optimal solution to maximize your efficiency. Another one would be safety. So if you have an autonomous car, of course, you don't want to pass very close to people on the street. So you want to have maybe a certain distance to them. And so safety is, of course, super important, not only with cars, but also in a factory. You don't want to hurt anyone. And another could be coverage. So for example, if you want to use a lawnmower robot, then of course you don't want it to randomly cross your grass all the time, but you want to have it covering in an optimal way so that it finishes as soon as possible. So those are some reasons why we want to have optimality. Just to summarize, aesthetics should look good from an observer perspective. We want to have time-optimal paths because they are efficient. And it should also keep distance to prevent collisions, especially with humans. And in some cases, you also want coverage, that it should reach every point of your workspace, but it should not, for example, reach it twice or spend too much time to move around. Okay, and there is actually one more reason why we want optimality. And this comes actually from something which we already discussed with search-based planning, namely that optimality principles often help us to search more efficiently. And if you remember the A-star algorithm, where we had this heuristic, bless you, where we were prioritizing the search for best cost paths, and we were doing that to outperform, for example, brute force search. And this was actually a very good way to solve problems, because you first try out what is actually the optimal solution and try first those paths, and then you are going down in the solution cost, and this gives you first the optimal solutions, and is a very efficient way to actually search. And we also did used it for pruning using the necessary conditions. So for example, if you already know that you have found a path which has a certain cost, then you can often use it to prune other paths which are possible. And this gives you already a very good idea in which direction you should, for example, sample your space. Okay, any questions? Okay, then let me talk a little bit more about this cost framework which we use in motion planning. As I said, we need to define a cost function for our problem. And because we are usually operating on graphs and on paths, for your motion planning algorithm, you need to actually define 3 parts of your cost. You need to define a cost for a single configuration, you need to define the cost of an edge, and you also need to define the cost of a path. So there are 3 parts which you have to define for every cost function. So let me show you some examples. So for example, if you want to have the shortest length of something, you might not have a cost associated to a configuration. That would maybe be 0, but you of course would have a cost associated to edges, where you would take the length of a segment, or you use the metric distance. And the path cost could be defined as the sum of edge costs. So I would say this is a very standard way of how you could define a cost. You just want to have the shortest path in your configuration space. But as I said, there are also other reasons why we want to have optimality, and there are other costs which you can define. Another very, I would say common cost to define is maximum clearance, where you want to stay as far away from your environment with your robot as possible. And in that case, the definition of a cost would be that, for example, for the configuration, you define it as a distance from your robot to your environment. The edge cost in this case might be the maximum over all configurations on your edge. And then again, a path cost might be the maximum over all edges on your path. And I will show you an example shortly of that one. And then, of course, you could have other cost functions, for example, lowest energy, where you have configuration cost of 0. And then an edge cost might be the energy you need to spend to go from A to B on an edge. And a path cost might be just the sum of edge energies. And something which you need to actually keep in mind for sampling-based motion planning is that most of the planners which we will look at, they require actually an additive cost. And an additive cost is basically a cost where you can basically sum it up from different segments. So for example, if you have a path here from A, B to C, then an additive cost is basically sum where the cost from A to B and the cost from B to C both sum up to the overall cost to go from A to B to C. And so if you don't have an additive cost, you can't actually use all the sampling-based motion planning algorithms which we will talk about. So this is something which you need to keep in mind. And here's an example of something which could be a non-additive cost. For example, you could define the number of objects manipulated by a robot manipulator. This would be basically an example of a non-additive cost. And another one, which I think makes a lot of sense, is an average clearance cost. So for example, if you have a path here, let's say again from A, B to C, and you have an obstacle in gray here, we talked about maximum clearance, which would be the maximum distance from your path here to your obstacle. But you might also want to have something like an average clearance, where you just take the average of all the clearances here to your obstacle. And this would be non-additive. So for example, here on this edge here, the average of all the distances, it might be 2.3, and all the averages here on the other edge might be 4.5. But if you just sum it up, you get a different value than if you take actually the average over all the possible clearances here, which would be 3.4 for this example. So this is, again, a cost function which is non-additive. And so, for example, you can't use it, but you could, for example, still use this maximum clearance function. OK, just to recap this, what we actually want is the best possible motion. And why do we want it? Because it helps us for aesthetics, efficiency, safety, coverage, and also optimality for efficient search. And the way of how we do it is that we define this cost framework, and we are taking special care that we have only additive costs. OK, any questions for that one? OK, then let's go to how we can actually solve it with tree-based motion planning in an optimal way. So let's first talk about this RT algorithm and optimality. And one question is, what if we actually keep running RT? Would we actually improve upon our current path? And the answer is actually no. So let's look at this example here. You start in the middle with a point robot, and there's a goal region up here. And if you just randomly explore your configuration space, then at some point, some configuration of your tree will actually hit this goal region. And in this case, you just backtrack, you have your path. And then if you just continue extending your tree and letting RT run, you get a finer grained tree here. But you can see here the path found by RT, it's still there, and it's not actually improving. So you get a finer and finer tree, but you still have this path here. And this path is not optimal in any sense because, of course, you could just have a straight line here, and you would have solved the problem in an optimal way. And so one question would be, what causes this actually? Does anyone have an idea? Yes?
Well, because the tree can't have loops, and because we've already found a path, there's no way to shorten the path, because that would mean finding a loop.
Yeah, that's true. And also, of course, yeah, edges are only added and they are never changed, so there's no rewiring going on, and the reason for that is, of course, that you would maybe introduce a loop there. Okay, but there is a way to make it actually optimal, and this was invented in 2011 by Karaman and Frassoli. So they published this paper here, Sampling-Based Algorithm for Optimal Motion Planning. It is widely cited. I think this was like 2 years ago. I think this went up to like 10,000 or something now. And they proved in their paper that RT is actually suboptimal, which means that the cost of the best solution returned by RT converges to a suboptimal value, and it does so with a probability of 1. And yeah, so basically if you let RT run and you let the number of samples go to infinity, then you are guaranteed to find a suboptimal value. You will not find actually the global optimal solution, which yeah is pretty obvious, but I think they were the first which actually gave a mathematical proof of this. And they also gave another algorithm, which is RT, but with some rewiring going on, and they called it RT star. And the pseudocode here is shown in this picture. So yeah, it looks pretty big, but if we just go into the details, you see that it's basically just RT plus a little bit of rewiring. So what you can, wait a second. Yeah, what you can still see here up here, the pseudocode looks exactly like the pseudocode which we saw in the first slide on RT. What we do here is that we sample a configuration in your configuration space, we find the nearest in your tree, we steer the tree towards this new configuration, and we have this parameter mu here, which tells us how far we should actually steer our tree. And so nothing new here, but then at some point, once you have actually found a new edge between your nearest and your new configuration, there's a new function here, which is a rewiring of the tree. And the way of how this works is actually that you are trying to find out if there is a neighbor of your new point which you want to add to the tree, which gives you a lower cost to reach it within a certain neighborhood. And so in this pseudocode here, this is exactly what is done. So instead of just connecting, you first check what are actually all the nearest configurations to my new config here. You call it here xnear. You also add this new configuration to your tree. And then you compute the minimum cost and the minimum configuration from all your neighbors. So in the beginning, you just set it to your nearest one, which you have just connected to. But then you actually iterate over all the neighbors. You check if there is actually a collision-free connection. And if there is, and if the cost of this connection is actually lower to reach this new configuration, then you actually set the new min and min values here for cost and the configuration. And so in this way, you actually don't add an edge between your nearest configuration in your tree and your new configuration, but instead you search for all the neighbors, and then you take the neighbor which has actually the lowest cost to reach this new configuration, and then you add in the final step the edge towards this new configuration. So yeah, a a bit bigger piece of code, but in the end, actually a very simple operation where you just search the best neighbor and you connect it. And there's also a second rewiring going on, where you take the new configuration as a parent, and then you try to make connections to all the neighbors. And this is done to actually reduce the cost. So this is basically just the inverse of the previous operation. So you take, again, your new configuration, which you have just found. You compute all the neighbors. You compute if there's a collision-free path to them. And then you check if the cost to reach them over your new sample is lower, then you actually add a new edge to your tree. Okay, so this is all theoretically here in the pseudocode, but yeah, let me just show you some visuals to show you how this actually works. So here we have, again, a small 2D planning problem. We have in green here some obstacles, and we have two configurations for a point robot. It has to go here from the top configuration to the bottom configuration, and the motion planning problem is that orange is Q start, and this one here is Q goal. And then you do the same as we did with RT. You start here from the start configuration, you sample random configurations, and you try to connect them. And so at some point, for example, you have this intermediate tree, and you have a new sample configuration Q random, which is in purple here. And so the nearest node here in your tree might be this configuration here. And then with usual RT, you would just connect it. But in this case here, the new edge is actually not valid, so you have to reject it. So this is one way of how this could work out. And then later on, you might have a different tree here. And we want to look at one of the rewiring operations. Let's say you have sampled a configuration here, and your nearest neighbor in your tree is here. Then before you actually add this edge here, you check all the neighbors from this configuration. So this is the rewiring step now. So yeah, we had this here. This is the new configuration, and this one was the nearest configuration. And now we search for all the nearest configurations around it. And we check if there is actually one of the nodes from which, when you go from the start to this node, you get actually a smaller cost. And we find one here, where basically you have a shorter distance to reach than when you actually go from the nearest here. And so this is basically the first step of this rewiring operation, where you add an edge here and you don't add an edge here in this configuration. And then the second step of this rewiring is basically that you look again at all the neighbors, and you try to find out what would be actually the neighbor where you would have the shortest distance to reach. And so, for example, in this case here, you would add an edge because it's faster to reach this configuration here over this path instead of like going to this configuration and reaching here. And you do that usually for all the neighbors here. And so in that way, you do a second rewiring step where you again reduce the cost of this whole tree to reach a configuration. Okay, and just to give you a more, I would say, simpler pseudocode for that. This is basically here. You can also define this rewiring operation just by computing all the neighbors and then doing these two rewire steps from all the neighbors to your new configuration or from your new configuration to all your neighbors. And this rewiring step is just that you steer from one configuration to another. You check if it's constraint-free, if there is collision, and then you check if the cost is actually lower, and then you set the parent here to X. And yeah, for a tree, you don't explicitly have to add an edge, but you just set the parent here. And so this one would basically be the same as this pseudocode here, just rewritten a little bit better, because this pseudocode here is from the original publication, and so in the meantime, people actually analyzed it a little bit more and simplified it a bit more, and so this leads to here. Yeah, you had a question?
I have a question because, like, for me, this looks a lot like just path shortening. No, not entirely, but like in the spirit, I guess.
Mm-hmm.
So, and with the path shortening, we went from just a single path that we already knew and then just shortened that. And for me, this seems like a lot more efficient than doing this all the time with the entire tree. So, why is this an improvement upon that, or is it
Mm-hmm.
even an improvement?
Very, very good question. So with path shortening, you will actually converge to a local optimal solution. And with this one here, you will actually converge to the global optimal solution. And so if your initial path was very bad and I don't know, so maybe I want to now walk to the Brandenburg Gate or so, and I find a path which goes all around Berlin, then with path shortening, you might not actually shorten it so much that you actually reach the global optimal solution. But if we just do it with RT star, then it would give me the optimal solution in the end. Of course, only when the number of samples goes to infinity, when time goes to infinity, you will actually also end up with the optimal solution. But yeah, very good question. And this is also one of the big difference between sampling-based planning and optimality and optimization-based planning, what we will talk about later on in the course. Okay, yeah, and so this one would be the most, the absolute minimal version of pseudocode, which you can actually add to make this RT algorithm, which we had in the beginning, asymptotically optimal. So basically, we just have this rewire operation, which I defined here. We just added after we found a new configuration and we found a new connection. And by just adding this rewire operation, we made this whole thing here reach a global optimal solution in the limit. Okay, so now let me show you some visuals again. So this is, I think, still from the original paper from RT star. In the top row here, you can see again the performance of RT. So we find a path, and then we just are stuck with this path, so the tree will not improve. If we actually take the same sampling configurations, but now we start here with RT star, then you will also get almost the same solution here. We get this zigzag path here towards the goal. But now, because we do this rewiring, over time, the tree will always be restructured in such a way that it always shows you the shortest path to every configuration. And so through this rewiring, we also always find like a new path. And the path is actually improving over time. And you can see here, the more samples we find, the better actually our estimate of the global optimal solution becomes. And then in the end, when we have actually a very dense covering of the configuration space, you can see here we have also found an almost optimal solution. And what you can also see here is that the tree shows you basically for every point also an optimal path towards this point. So it's really a tree of containing only shortest paths to all the points in the configuration space. And any questions about this one? Yeah.
I mean, I think it's interesting that this has like no notion of orientation integrated, so it will like really take forever to find a straight line. Because
What do you mean with orientation?
always will, because we're randomly like trying to find this direction with like random samples, right?
Mm-hmm.
So like just to find a straight line, it has to basically like sample infinitely just to find enough
Yeah.
That's okay. But I'm even sure there's improvements on this.
That is correct, yeah. Yeah, but this is basically the basic idea, and it was a very powerful idea because with this one you can actually prove that you reach the global optimal solution, and not only like a local optimal solution, and not only like a feasible path, but you will actually improve this path over time if you let it run indefinitely. And here are also some examples of where we can see that this path is also not constrained to be like locally optimal, but also globally optimal. So this is very similar to what I talked about earlier, that if we find, for example, with RT a path which goes in the wrong direction and then we want to do path shortening, we will just locally improve it, but we will not like make big jumps in the configuration space. And so this is exactly where RT star can actually still find an optimal solution. So we have here, again, very simple environments, the same as before, but now we have also in red some obstacles. We let, again, we grow our tree here, we find an initial solution towards the goal region. And so this one would be returned by RT, and we could maybe do a little bit of improvements here, but we would never find actually the real global optimal solution, which would be the one which goes up here and then reaching the goal region. And with RT star, we see here again local improvements, but the more the tree actually grows, at some point you see this big jump here between one of the local solutions here to another local solution, which is the one which goes actually above here because it has a lower cost. And then when we grow and grow the tree, we can see that the solution is actually improved and improved until we get very, very close to the global optimal solution, which is actually to go up here and then directly to the goal region. And so this is a big difference between all other algorithms and RT star because it can make those big jumps. Yeah, please.
This goes back to what Max asked, like why don't we just limit the rewiring to after we've found any solution?
Mm-hmm.
Wouldn't that make sense? So that we at least know that there's a solution?
Yeah, that makes a lot of sense, but this is not the way of how RT star works. It basically already does this rewiring in every iteration, and the reason why it does it is that even in the beginning it still rewires the tree, and if we are just doing this rewiring after we found a solution, we would need to go over the whole tree and have to rewire it completely again, and that would be a very big operation which you have to do. But of course it could be a good idea to do that. You are first just trying to find a feasible solution, and then when you find one, you do this big operation where you rewire the whole tree which you have just found. But it is very costly to do. And I don't know if you can actually still prove that everything works correctly, but I think it would not be a problem. But yeah. So they just opted for having always like the optimality in the tree instead of like doing this big rewiring operation later on. As you can see here in 2D, the first time we find a solution, we have already a very big tree, and then if you have to actually go over all the nodes here again and all the edges and do this optimality rewiring, it might be a bit costly. And if it's already here costly, then in 10, 20 dimensions, it might be something which takes another hour or so. And yeah, it might be actually more efficient to do it in every iteration to always keep the optimality. Yeah. Okay. Basic version, any other questions? Okay. And what the authors of RT star actually proved is that this algorithm is asymptotically optimal. And asymptotically optimal means that the probability that the solution cost of RT star is not more than 1 plus epsilon times c star is 1 as the number of iterations goes to infinity. So epsilon is some arbitrary small number, and the probability, and c star is the cost of the optimal solution path, of the global optimal solution path. And the probability that the distance between your iteration number n minus your optimal cost is bigger than epsilon is 0 for any epsilon when n goes actually to infinity. So basically you can choose any epsilon, the small s you want, and then you can find some n for which you can actually show that you will have found the optimal solution if one exists within this epsilon radius. And so this is a very powerful property of this algorithm. However, there is no mentioning of convergence rate, and the convergence rate is actually unknown, so we don't know how fast this will actually converge. Which is, of course, not so good, but at least we can already prove that we will converge to the optimal solution. Okay, and now I want to explore some questions and show you some ways of how you can show that those are actually optimal and complete. So first we will ask why is actually RT probabilistically complete, which means that it will find a feasible solution if one exists. And then we will look at why RT is not asymptotically optimal, and then why is actually RT star asymptotically optimal. I think those are the next big questions we should ask. And this brings us first to a probabilistic completeness proof of RT. Before I start here, any more questions about the basic version of RT star? Before we go here into proving some properties. Okay. Right, so the next plan is now that we first analyze RT, why it always will find a feasible solution if one exists. Then I want to show you why it is not optimal, and then I want to show you why RT star is actually optimal. And what is actually the reason why it will find or converge to the optimal solution. Okay, so let's first talk about probabilistic completeness. Let's recall that a planar is probabilistically complete if it finds a solution if one exists. So this is a basic definition. And the main proof that RT is probabilistically complete is based on induction. And it requires that the number of samples goes to infinity. And to do this, I want to show you a small proof sketch. The whole proof is actually given here in this publication, which is called On Probabilistic Completeness and Expected Complexity of Probabilistic Path Planning. So this one gives you a very formal proof of how you can actually show that you will find a feasible solution if one exists. But I want to show you just with some visuals of how this actually works. First, we need some assumptions. There are 3 assumptions. One is that you have to have a feasible path. So if this is actually not solvable, then RT can't do anything. So we need to actually have this assumption that there exists a feasible path. Then second, we need to assume that this path has epsilon clearance, whereby epsilon can be some arbitrary number bigger than 0. So you can't have cases where the path is actually touching the obstacle or going like in a 0 distance way around obstacles. And the third one is that your sampling, whatever sampling you do, is dense. And so usually if you just do uniform sampling of your configuration space, then sampling will be dense. So this is usually also not a problem. And if you have those assumptions, then you can actually show that RT will find you a feasible path in your configuration space. yeah, I just wanted to show you here sampling is dense, meaning that you will cover every point here of your, or every small disk which you can define here, you will cover in the end when the number of samples goes to infinity. Okay, and so the proof basically has, yeah, I think 3 or 4 steps. So the first step is that you cover your feasible path with delta space disks. So you take your hypothetical feasible path, you just cover it with a lot of disks here, and then you do an induction on those disks. And this induction basically says that first you will reach your first disk in your sequence, and then with induction you need to show that if you reach your nth disk in your sequence, you will reach the disk n+1. And I just want to show you how this works. So for induction, the induction step means that you have to reach the first disk or ball in your sequence, and so this base case is trivial because you are starting at your start configuration, so your start configuration is always like part of your tree already, and that is why this is trivial. And so what is not trivial is to show that if you reach the first ball here, the ball number n, then by induction you can actually reach ball n+1, and this is something which we need to prove. And so what we can assume, and this is usually how you do this induction, is that you have reached ball n here with your tree. So there's some kind of structure here from your tree, and at some point you actually reach the configuration here. You made an extension to this ball here, and now you have to show that you actually reach the next ball. And if you can do that, then you can actually show that you can reach all the balls here in your sequence, and you can find a feasible path. And the first step for this is that you have to show that at some point you will sample in this next ball here. And this is always true because your number of samples goes to infinity, and your ball has a certain measure, so that it has a certain size here in your configuration space. And you can be sure that with probability 1, at some point there will be a sample in this ball here. And if this is true, that you will find at some point a sample here and you have reached your last ball here, then you can also be sure that there exists a valid connection in free space because you have just covered your whole feasible path here with disks, and all those disks are also feasible. So there's at least one connection here. And this shows you that you can construct a path which is what we call delta similar to the path which you have defined here as a feasible path. And because you can do that, you have just found one feasible path which solves your problem. And so in summary, you need first those 3 assumptions here, and you need to make sure that you have a feasible path. You need to make sure that it has an epsilon clearance so that you can put some disks on it. And then you have to also assume that your sampling is dense. And then this proof, as I showed you, is just that you put those delta space balls onto the feasible path depending on your epsilon. So if your epsilon is very small, you need to also have very small balls or disks on it. And then you just execute this induction proof that you first prove that you've reached your first ball, which is trivial. And then you show that you can reach ball k plus 1 from the kth ball. And this is basically the main part of the proof. Does that make sense to you? Any questions about it? Okay, then I have a question for you. What if we actually replace feasible path with optimal path? Would the proof still hold? Anyone an idea?
Just an idea, but I think the problem is that the proof as we have it right now only
Mm-hmm.
And then by induction, the next disk is also visited.
Mm-hmm.
But we need the disk, like the first disk, to be visited immediately,
Mm-hmm.
so that the next disk is also visited immediately, and not from like some other part of the path, but from this part.
Yeah, that's exactly right. So there's actually no guarantee that you make actually a connection from ball k to ball k plus 1, because there might be a different nearest neighbor, because you have this randomly exploring tree, and in the end you can't actually prove that you have exactly reached from k to k plus 1. And this is why this is not an optimality proof. And another question, of course, is can we fix this? How do we fix this so that we can actually reach optimality? Any idea? I mean, you gave almost the answer already. So
Not really sure.
well, so the answer is actually that we need to show that we are always reaching the next ball from your last ball, basically. And we're not reaching it from any random configuration, but that we have really this succession of reaching the right configuration, and then we can just do the same proof, but for an optimal path, and then we can be sure that we have actually followed this optimal path closely, and that we reach, yeah, a path which is very close to it. Okay, and that is what I want to show you now. So a small asymptotically optimal proof for RT star. And yeah, the idea is very, very similar to the RT case. You need to assume, in this case here, that we have an optimal path, and that this optimal path has some clearance, again, some epsilon clearance, and this can be as small as possible, but greater than 0. And again, you need some dense sampling, of course. And yeah, as said, RT might find the wrong wiring. So for example, you find a sample here, but then your nearest neighbor might not be the one in the last ball here, but something outside, and then you just connect it here, and in this way you don't find the right succession here, but instead you find a different feasible path. And RT star actually considers all the neighbors for rewiring. And because it does so, it also computes the cost to come from all those points here to your new sampled configuration. And in that way, it can actually make sure that you have reached your new configuration from the previous ball, because yeah, the path to reach here is actually also optimal until this point here, because we have this optimal rewiring of the tree. And yeah, reaching this point here from out here will not be one on the optimal path, because we know the optimal path is actually the one here, which we have just covered with disks. And because RT is rewiring this accordingly, it can actually make sure that we stay very close to the optimal path. And we can basically show that we always reach the next ball from the previous ball. And that is the reason why we can actually show optimality. And then you might remember that in the pseudocode which I showed, there were two rewiring operations. First, we tried all the neighbors, and we tried to find what is actually the shortest cost to come to reach our new sample here. This was the first rewiring operation, and then there came a second rewiring operation where we did basically the inverse. We tried to find out what are actually the cost to actually reach all the neighbors here from your new configuration, and we did some rewiring again, yeah, to have the shortest path here to each of the neighbors. And there's, of course, a question. Do we need this second rewiring step for optimality? Or is it enough to have just the first rewiring step? Anyone an idea? Yes.
I think it's needed for optimality because we could still track into a later path, a later ball on the optimal path, and we would still connect it at this later point optimally. But then to find the optimal path, we would have to go through this ball again. And in that case, we need to rewire it to have the actual shortest path.
So what do you mean with the later ball? Do you mean like the second one here?
We reach, for example, ball 1 and then we reach ball 10.
Mm-hmm.
And if we reach ball 10 before, like in the round path without reaching 3, 4, 5, 6, 7, 8, then like we will have gotten to ball 10 in a suboptimal path.
Yeah, but I think this would be actually taken care of by the induction assumption that you can, because you can show here that you can always reach the next ball. You could also say that you will at some point reach ball 10 from ball 9 because of your induction assumption, because you need to at some point reach ball 9. And also you can go all the way back. You can say, of course, you need to reach it from ball 8, from ball 7, and so on. And this would, again, take care of it. You agree, or?
But then there wouldn't be a connection between ball 9 and ball 10.
But it has to be because of this induction step which we just did. So we basically said, okay, we will always reach ball 10 from ball 9 at some point. So, I mean, it can definitely happen that you reach it first, but then still at some point you will have reached ball 9 and you will need to again sample in ball 10 at some point later on, and then you will again find a connection there. So even if you have already something there, you will come back there because you're sampling indefinitely, and you will at some point again reach it, and then you will have another connection there. So everything is rewired at some point, so even if you have made a wrong connection at some point and you reached a different ball first, you will come back to it later on. Yeah. Okay. And yeah, so basically we don't necessarily need it, but it improves definitely the cost because it locally rewires here again the points. But for the proof, you don't necessarily need it. So you could actually get away with one rewiring step, but if you just do it in practice, then you will see that it takes much longer time to converge. Okay, so that was everything for the proof of RT star. Any more questions about it? Yeah, please.
Like, isn't RRT by itself, if you ran it like infinitely many times, wouldn't it also always find the optimal solution?
You mean the classic one?
Yeah.
Why?
Because I think if you ran it infinitely many times, it would find every path. Every possible path.
Well, so I think this picture here, sorry. Yeah, so this one was basically when we were running RT infinitely many times. and it was never actually improving the path here.
No, I don't mean like infinite iterations, but infinite, like from scratch, infinitely many iterations of RT.
Oh, you mean you restarted?
Yeah.
Oh. I would say yes. But yeah.
I just thought about the same, and I think the problem is that we have no stop condition other than for RT star, because how do we know that we actually found the optimal path then?
You mean for RT, for the classic one?
For what we just suggested.
But do we have a stop condition?
Yeah, I think the stop condition in this case would be just we found something, and then we just return it. And if you just do that infinitely many times, then I would say it will find, I don't know if you can actually prove that it will find every path. But yeah, I mean, a very simple algorithm would be just that you rerun it and you check if the cost is smaller. And yeah, I don't know if you can actually prove that you will reach the optimal solution. I don't know it, but yeah, I mean, at some point, you will have just a sample which is exactly here in the middle, and then you will connect it here, and you will have another sample here, and you will connect it, and I think it should be correct. So you should actually converge to the optimal solution. Because you will have, at some point, there will be a sampling sequence where you have always all the points in the right order on the optimal path. So it will be very lucky to get there, but I think if you run it infinitely many times, then of course you should get there, yeah.
But here, like in RT star, don't we add like a lot of additional collision checkings for these neighbor checks? So isn't it in the end just like a trade-off of like increasing probability of finding the optimal path, and you're trading it off for a lot more like computations of the collision checkings and so on?
Oh yeah, of course. So it's slower.
Do we have an end condition here? Like we don't know if we reached optimality, do we?
No, we don't.
Yeah.
But of course, you can have like convergence end conditions where you say, okay, I haven't improved my path for the last 1,000 iterations, so now it would be time to stop. Or in this case here, you have reached a path which is very close to the theoretical limit of solutions, because you could say, okay, what is my distance between this point and my goal region? And this would be the lowest possible cost. And if you come very close to it, you can say, okay, it cannot get better.
But we could do the same with the normal RT, just calculate, I don't know, 10 or 100 paths and then compare the costs.
Yeah, I mean, you can definitely do that. But in very complex scenarios, you really need to have all the points sampled along this line here. And it would be very, very lucky to get there. You will get there, but it would be taking a lot longer than just running RT star.
Yeah, I just had a question regarding how the rewiring operation scales over time. So in my mind, you have the more neighbors, the more refined our path is. So the rewiring step at some point will take a lot longer than at the beginning, right?
Right. This is absolutely true. And that is why there is a very complex formula to actually compute how many neighbors you want to compute in every iteration, so that you are actually not having too many and not too few. And so the formula here is actually the one here on the lower right corner, which is basically the neighborhood radius. And this one depends on your tree size and your dimension. So V here is the tree, and the absolute of the tree is basically the number of nodes in your tree, and D is your dimensions. And lambda, no, I don't know how it's actually called, but this one is basically just a parameter where you can tune this a little bit. But this is basically the formula which they have shown in their original paper to scale very well with the number of dimensions and also the number of nodes in your tree. And so this is how they actually keep it in check. But yeah, very good question. So this is definitely a big problem, and I think it took a lot time to actually come up with this correct formula. Okay, any other question? Okay, then let's go to our last topic, which will be informed optimal planning. So there are a bunch of problems with RT star, and I want to just highlight two of them. You can see here, this is one run of RT star where it converges very nicely to the optimal solution. But there are some things which don't really make sense with RT star. So one is that it's not prioritizing the best cost paths first, like in A star. So for example, if I'm starting here and I just grow in all the directions, I would say, why are we not just checking first that the straight line distance here is the best solution cost, right? So it makes sense to first try out those, because they would give you basically the optimal solution, and why are we not trying first those, and then we can just go with our tree in different directions. So this is the first problem, and the second problem is, in this case here, in this iteration, we found a path to our goal, and then instead of like improving this path here, RT star is just growing the tree in all directions of your configuration space, and you sample still in the lower left corner here, and you still rewire your tree in the lower left corner, and you do that all the time, and you get this nice tree here which covers everything. But really in the end we don't need all those configurations down here. They don't make sense, because we already know that there's a path here, and all the configurations out here, they cannot actually lie on an optimal path if we already found a solution here. So those are two big problems, and they make RT star super inefficient. And luckily there are some solutions to it. So yeah, as I said, it's not prioritizing paths as A star does, and once a path is found, it still samples regions which cannot improve solutions. And one solution to those problems is actually informed sampling. So informed sampling restricts sampling to regions which can still improve solutions, and it is based upon this concept of an omniscient set. So what is that? Let's first talk a little bit more again about cost to come, cost to go, and F value. You might remember this from lecture 3 and 4 about A star. So optimal cost to come, G, is basically the minimal cost to go from start to configuration. And then the optimal cost to go, H, is the minimal cost to go from a configuration to your goal. And then in A star, you had this F value, which is basically just the sum of cost to come and cost to go. And this is basically the minimal cost at a state X, where you are constrained to go through X from start to goal. And the definition of an omniscient set is basically given here. So let's say that we have a cost C of our current solution. So you found a path, you have a solution cost, and then this omniscient set is basically contains all the configurations where the optimal F value of a configuration is smaller than C. And so those are all, so the question for you maybe first, what does this actually represent before I tell you this? Anyone an idea? Yes.
Like assuming that we are working with Euclidean distance,
Mm-hmm.
is this just an intersection of two spheres, or
Mm-hmm.
which I imagine is a circle,
Mm-hmm.
two-dimensional space, and then from the to the goal is the cost to go, and so like in my mind this is just in each section.
Yeah, I think you're already one step further. So this one is actually having the optimal cost to go, which is also taking all the constraints and all the collisions into account. So this would not be as a circle anymore because, yeah, not everything in the circle might be feasible. But yeah, so you could actually think about the set as all the configurations which lie on a path with this f value here. So the f value, I think it's best to visual or to think about it as the cost of the optimal path which has to actually go through x. And if this path, this optimal path which goes to x, it has a lower cost, then it can actually still be one of the configurations which lies on an optimal solution path. And everything which is outside there, it cannot be on an optimal path because the optimal path through this node here, it's bigger than c, and then yeah, it cannot actually improve the solution cost anymore. But of course, you can't explicitly compute it because you don't know the cost to come and the cost to go without computing it. And so what people have actually done is that they came up with this informed set, which is very similar, but instead of having this f value, you take the f hat value, where h is actually just replaced with an admissible heuristic, which underestimates the cost to go from your current configuration to your goal. And yeah, for the Euclidean case, and where your metric is actually an L2 metric, you can define this admissible informed set here in this way, where you have just the distance between start and your configuration x, and your distance between x and x goal, and they summed up is the f value, and it should be smaller than c. And c is, of course, the best cost which you have found so far. And yeah, geometrically, this is a prolate hyperspheroid for with the L2 metric in Euclidean space. And here are some visuals. So let's assume that we are in 2D space. There are no obstacles. We have, again, start and goal configuration. We found a path. The path gives us a certain cost. And with this cost, we can define this informed set. And this informed set is basically just this, this ellipsoid. And everything outside of the set cannot really contribute to an optimal path. So we can basically just say, OK, everything inside of the set can theoretically be a non-optimal solution, but everything outside cannot be a non-optimal solution. And then every time we improve our path, we can also improve our informed set. And yeah, we can do that until we actually find here the straight line. And we can also see that the informed set collapses to this ellipsoid between the 2 points. There's an algorithm informed RT star, which uses basically this informed set. And there's also an improvement, which is called bit star, which grows an informed set to be more efficient also in the beginning. So in the beginning, you start by just prioritizing certain paths which have a potential optimal cost to go. And this is how it looks like in practice. So we have this ellipsoid here in 2D. Black are obstacles again. And so in the beginning, we start with a certain size of this ellipsoid, and we grow it, and we only try to make connections inside of this ellipsoid. And we grow it until we actually find a solution. And once we found a solution, we know that everything outside cannot contribute to our improvement. And then we just sample inside. We try to improve our path. And this basically shrinks our ellipsoid again. And it does so until we actually find the optimal solution in this case. OK, drawbacks are that this only works for shortest path cost, and it only works in Euclidean space. And yeah, but this is a very nice way of how we can overcome those two problems with RT star. Yeah, you had a question?
If you had like a, I don't know, weird obstacle, like I don't know, like a spiral or something on the bottom that it would go through initially, then I think it like would still work.
Well, they actually proved that this works, so it will work.
Okay.
But yeah, a spiral.
Well, like
I mean, yeah, it should still work. Because you need first a solution, right? And so the solution would be just something which tries to go out of the spiral. So the solution cost would be a lot larger if you have like the spiral solution cost. And the ellipsoid would only shrink if you actually improve your solution cost.
But imagine like if the image on the right, there was a spiral where it goes through
Mm-hmm.
when it comes through the bottom,
Mm-hmm.
but actually would have been easier to go. Would it still find this that it doesn't go over the top? Because it wouldn't shrink because it would still have to.
Yeah, so it would only shrink if there's actually, yeah, so I mean it shrinks depending on the solution cost, right? So the solution would always be inside and the cost would always define the distance here. Okay, yeah, let's wrap it up. So we talked about asymptotic optimal planning and especially tree-based planning. And yeah, especially we talked about RT, RT star, and a little bit of bit star. And next time we will extend this to kinodynamic systems and we will look at two algorithms, AORT and SST star, which use different strategies to do asymptotic optimal planning, but for kinodynamic systems. Okay, that's everything for today. Thank you very much.